Pressing a key feels instantaneous, but that motion triggers a high-speed 7-layer sequence through material science, micromechanics, and digital logic. The first point of contact is the plastic. Keycaps are typically injection molded from two distinct plastics with wildly different chemical properties. If you recognize these building blocks, you're looking at ABS. It is cheap and easy to mold, but it is extremely soft. The natural friction and mild acidity from human fingers act like sandpaper, polishing the plastic to a greasy mirror finish. To resist that wear, premium keycaps use the much denser, heavier PBT plastic. Beneath the plastic sits the engine. A standard $15 office board relies on a continuous sheet of molded rubber domes, forcing you to push all the way to the hard plastic base to register a letter. In a premium board, every single key has an independent microscopic engine with a sliding stem and a coiled metal spring. As you press, tiny plastic legs brush past two gold-plated metal leaves, pinching them together to complete the circuit. These physical engines dictate the acoustics, the friction, and the resistance of your typing. But without a way to translate those mechanical pinches into digital data, they do absolutely nothing. Wiring all 104 individual keys directly to a central processor would require a massive, expensive tangle of cables. Instead, engineers map the keyboard using a switch matrix, a simple grid of horizontal rows and vertical columns. The keyboard's brain sends a continuous pulse of electricity down the rows. When you press a key, you close the circuit at a specific location. The controller detects the exact intersection, say row 2, column 4, and instantly knows you type the letter T. This grid system creates a major vulnerability. If you press multiple keys at the exact same time, the intersecting electrical paths collide and confuse the controller. Pause the video for a second and look at this 2x2 section of the grid. If you press 3 of these corners simultaneously, where does the electricity go? The current flows backward through the unpressed 4th key, registering a phantom keystroke, an error called ghosting. High-end keyboards prevent this by soldering a microscopic one-way valve, a diode, next to every switch, strictly forcing the electricity to travel in one direction. By solving a physical wiring problem with the grid, engineers created a logic problem, which then required a hardware intervention to fix. Completing that circuit is a violent event. At a microscopic level, those two gold leaves do not touch cleanly. They violently bounce and vibrate against each other for several milliseconds before settling. This graph shows the raw electrical output of that physical collision. To a highly sensitive microcontroller, that microscopic vibration reads as an erratic, stuttering signal, meaning a single press of the A key would register as a half-dozen inputs. To correct this, the keyboard relies on a debounce algorithm. The software forces the controller to wait a few milliseconds after the initial contact and simply ignores any secondary spikes until the physical metal stops vibrating. Once the signal is clean, it is sent to your PC. Modern keyboards run this check at a 1000 Hz polling rate, asking the switches for an update 1000 times every single second to maintain a flawless 1 millisecond delay. We have complex debounce algorithms, microscopic hardware diodes, and 1000 Hz communication protocols, all serving a physical key layout that defies logic. In the 1870s, Christopher Latham Scholes developed one of the earliest commercially successful typewriters. Early typewriters used mechanical metal arms that swung up to strike an ink ribbon. If a typist pressed two adjacent keys too quickly, the metal arms would collide and jam. To fix this, Scholes scattered the most common English letter pairings across the board, intentionally forcing typist fingers to travel further distances to slow them down. Because we still use this staggered 19th century layout, modern typists twist their wrists outward in an unnatural posture called ulnar deviation to reach the keys. To fix this biomechanical strain, modern ergonomic keyboards use ortholinear layouts, aligning the keys in perfect grid squares, so your fingers move in natural, straight lines. The next time you type an email, think about the stack of engineering beneath your hands. You are feeling the chemical resistance of dense plastic, triggering gold-plated mechanical engines, routing current through a diode-protected grid, algorithmically filtering microscopic vibrations, all while navigating a map drawn a century and a half ago.